Hello, calculus students. In this problem, we're going to analyze the behavior of this function f of x. And when I say analyze, we're going to look at intervals of increase and decrease, as well as intervals of concavity. So let's proceed. First thing we'll do is, of course, take the derivative of f of x, and that's fairly simple. The 3 and the 1/3 cancel out. Subtract 1 from that cubic expression to get a 2, so we just get an x squared. The 2 drops down, subtract 1 from the 2, we get a 2x, and then the derivative of x is simply 1. So we get an x squared minus 2x plus 1. And then f prime equals 0. Okay, we're doing that because, remember, we're looking for horizontal tangents. The first derivative gives us information about the slopes of the tangent line to this curve, and horizontal tangents occur when the slope of the tangent line is 0. So that implies that this expression will be equal to 0. And to find the points x where we have a 0 slope for the tangent line, in other words, a horizontal tangent line, we factor the expression out, keep it equal to 0, and we see that we get a repeated root at x equals 1. Right, so x equals 1 is a critical point. Sometimes people call that a stationary point. Let's create a sign chart over here, and let's plot that point 1 on our sign chart, and then analyze the behavior of f primed and f. So we'll look at the sign of f primed, and then once we know if it's positive or negative, we'll know if f is increasing or decreasing. So x minus 1 times x minus 1 is simply x minus 1 squared, and that quantity is always positive. So f prime is positive to the left of 1 and to the right of 1, so that means that f is increasing on both intervals, but it's somewhat stationary at 1. Okay, so that'll be interesting, and we'll explore that in a little bit. I like to draw these little lines here because these to me represent, I think of these as the tangent lines. So the tangent lines are sloping upward, and that means the function's increasing. Okay, now let's take a look at the second derivative, and just take the derivative of this expression here, and I get a 2x minus 2. F double prime is 0. That implies that 2x minus 2 equals 0. So now we just simply factor that out, and x equals 1 is the inflection point, which is also the critical point. Okay, so something funny is going on here, and you'll see exactly what that is in a moment. So let's do the sign chart for f double primed, and once we analyze the behavior of the sign of f double primed, we'll know what's happening with f, the function. So remember, if f double primed is greater than 0, then f is concave up. If f double primed is less than 0, then f is concave down. So 2x minus 1, we can use test points to the left of 1. For example, we could put in 0, and we'll get 2 times minus 1, and that's a negative number. And so that means we're concave down. And I remember that by just drawing this silly little picture here. So for negative, for the second derivative, we are concave down. Similarly, if we choose a point to the right of 1, like 2, then this expression for the second derivative will be positive, and it will be concave up. And I remember that by this silly picture. So to the left of 1, we're increasing, but concave down. To the right of 1, we're increasing, but we're concave up. So you can almost sketch in the air with your finger what this plot's going to look like, but I'll just summarize all this information and put the plot up here. So f is increasing for all x, so that's from minus infinity to positive infinity. F is never decreasing. It's concave down from x is minus infinity to 1. So here it is. It's concave down. And then it's concave up from 1 to positive infinity. So there it is, bending upward. That is an inflection point, but we also call that a saddle point because it isn't a relative max or min. This is an example where the first derivative test doesn't give us any information relative to whether or not this is a max or min. Here I drew a little tangent line so you can see if you're going up, like on the snowboard, you'd be coming up you'd be able to take a break here and then just try to climb your way back up the mountain. So that's why we call it a saddle point. All right, that's all the information we can gather from this function using the first and second derivative. Good luck.